Hello class, we are going over the slides for chapter 5 today. And we're going to start with standard deviation, which is one of the most important things in statistics is standard deviation. And you remember I defined it as the average distance points are from the mean, the data. So it tells you how spread out the data is, and it's very important because if we want to be able to compare things, we need to know the standard deviation. It tells you how far away it is. It's like a ruler for telling you how far away things are from the mean, from the average. And the most common measure variation, the standard deviation, plays a crucial role in how we look at that data. So another very, very important thing is going to be called the z-score. And what the z-score does is it lets you compare individual data values to their mean relative to the standard deviation. And you use this formula, z equals y minus y. That's the mean right there, the y with the bar above it. So if you want to write little notes next to this, y is a data point. Y bar is the mean. S is the standard deviation. And z is your z-score. And a z-score is basically how many standard deviations away are you from the mean, from the average. So we call the resulting values standardized values because we're making it a standardized value where it's the same for every distribution if you do this. So these are called z-scores. This is a very, very important thing in statistics, one of the most important things you'll learn. So standardizing with z-scores. The z-score is the number of standard deviations that a given data value is from the mean. It's how many standard deviations away are you from the mean. Like say the mean is 80. And one of the, like say this is test scores. And the mean is 80. And I have a data point, well, let's call the standard deviation 10. So on average, points are about 10 away from the mean. That tells you how spread out they are, how spread out the data is. And then I have a point at, let's call it 60. Somebody made a 60 on the test. So 60 would be y. 80 would be y bar, the mean, and 10 would be s, right? So how many standard deviations away is this 60 from the 80? It's 20 away, right? Which would be 2 standard deviations. 10 times 2 is 20. But remember, let's use that z formula now. Z is equal to y minus y bar over s, which is 60 minus 80 over 10, which is negative 20 over 10, which is negative 2. So that tells me it's 2 to the left. It's 2 deviations less than the normal, than the mean. So standardized values have no units to them. It's just standardized. A negative z-score, like the one we just calculated right here, tells us the data value is below the mean. It's lower than the mean. See, it's 60. That's lower than the 80, right? A positive z-score, see if I would have plugged in like 90 here, 90 minus 80 would have given me 10 over 10, it'd be 1. That means the data value is above the mean. So z-scores measure the distance of each data value from the mean in standard deviations. The mean for a z-score is 0, right? Because if if I had an 80 for the point, 80 minus 80 would be 0. And the standard deviation is 1 because we're dividing it by the standard deviation. And so it just makes it 1. So standard deviation is 1 and the mean is 0 for z-scores, for standardized scores. Standardized values have been converted from the original values to the standard statistical unit of standard deviations from the mean. That's what a z-score is right there. Standard deviations from the mean, that's a z-score. Thus, we can compare values that are measured on different scales. If everything's on a different scale or different units from different populations, we can all standardize it into a z-score and compare things. So yeah, it's hard to underestimate the power and usefulness of standardized scores. This is used in all of science when you're trying to prove a hypothesis, because later we're going to get into confidence intervals and hypothesis testing, and it all uses this. If you want to be able to prove something using data, z-scores are essential, and the normal model is essential. So you'll calculate them countless number of times, especially the final 3 units, like when we're putting everything together, you're going to use this a lot. Let's talk about how shifting the data changes things. When you add or subtract a constant amount to each value, it does the same to the mean. Like if you add 10 to every value, it's going to make the mean go up by 10, right? That makes sense. Because if I add 10 to every value, it's just adding 10 to the whole thing, which would be the mean, which means it's just going to stay plus 10. It's just going to do the same thing to the mean that it did to all the numbers. So this is also true for the median as well. So in general, adding a constant to every data value adds the same constant to measures of center and percentiles. Therefore, the center changes. Like mean and median all go up by the same amount. But spread does not change, because all you did was like shift it over. You didn't make it spread out anymore or anything. So IQR and range and standard deviation would all stay the same. Let's take a look at an example of that. This is a shift from actual weights to kilograms above recommended weight. So they subtracted 74 kilograms from each. So they're figuring out how far above or below the recommended weight you are, which is 74. So they're subtracting your weight from 74 from your weight. And all it does is shift this graph right here over 74 units to the left. So it looks like this now. 26 is the middle instead of 100. Well, the middle is more like, it's like close to 0 here, and over here it's like 70. See, it shifted it over. But your spread, your box plots will stay exactly the same. See how they look exactly the same? Because the shape of the graph didn't change at all. That's what a box plot's really telling you, is the shape of the graph. And it doesn't change at all, it just shifts to the left. So adding or subtracting numbers just shifts the data. It does not change the spread at all. So what is the center of the two distributions, and what is the IQR of the two distributions? The center, once again, is about 70, around here, 74. It's about right here, and in here it's about 0, because they made a shift to see how far you are from the average weight. And so all you did was shifted the data over by 74. The IQR stayed exactly the same. So the IQR would be identical here. The size of that box would stay exactly the same. Now we got rescaling data, which is different. It means you're taking every piece of data and either multiplying or dividing it. So all measures of position and spread both change by the amount that you divide or multiply it by. So if you multiply by 2, they're all going to double. If you divide by 2, they're all going to get cut in half. So let's take a look at that. So now we're going to rescale the data by multiplying by 2.2 to put it in pounds instead of kilograms. Because remember, to switch from kilograms to pounds, you multiply by 2.2. And look what it does to the data now. What it does now is it doubles every value. Like, see, the middle here is right around a little less than 80. Or right at 80, and the middle here is a little less, right at 160. It's basically doubling the data values. And if you look at spread, it's doubling. They're double the amount of spread out now. See, this is from here to here, and this looks about twice as wide now that we doubled the values. And look at that gap. See how it's a little more than 2 spaces right there? And that gap right there is about 1 space. That's because when you double all the values, it's going to double the spread as well. It would double the IQR, it would double the range. So the center of each distribution doubled from about 80 to about 160, and the range doubled. Look, we went from, let's see, 80, 100, 60. We went from about 50 to 160. So it's about 100 and something. And then on this one, we went from about 120 to about 360. So it's 200 and something. So see how it about doubled how far apart they are? And that's what it should do. A little more than double. It was times 2.2. And that's what it did. So let's get back to z-scores. What this means is that's what the z-score is doing. It's shifting the data by subtracting the mean, and it rescales it by dividing by standard deviation. And standardizing into z-scores does not change the shape at all. The shape doesn't change. It changes the center by making it 0. So the center change, and it changes the deviation, the spread, to 1. So it's giving you nice clean numbers where the center is 0 and the spread is exactly 1. And that's what it's meant to do. And if you standardize like that, you can compare all sorts of different data and get good information on it. Because they all have the same mean and standard deviation now, and it's a direct comparison. So when is a z-score big? Just think about it. Like, remember how I said on that test thing, the mean was an 80, and the standard deviation was 10. A data value that sits right at the mean would have a z-score equal to 0, right? Because remember, if it was 80, it'd be 80 minus 80 over 10 equals 0 if my score was equal to 80. A z-score of 1 means the data value is 1 standard deviation above the mean. So it would be like a score of 90. The score equals 90. A z-score of -1 is 1 standard deviation below the mean. So the score would be 70. And like a 60 would be 2 standard deviations. A 50 would be 3. A 40 would be 4 standard deviations away from the mean. So that's how that works. In general, a score that is bigger than 2 standard deviations, so like 60 to the left, right, and a -2, that would be considered a big z-score and kind of way away from the normal. So if you scored below a 60 on the test, you would know you're way off from the average. And or it could go the other way. If it goes 2 standard deviations to the right, if you scored 100, you're way above the average. So how far from 0 does it have to be interesting or unusual? So there's no universal standard, but a larger z-score is more unusual. Like I said, a z-score of 2 would have been 100, and a z-score of -2 would have been a 60, and those are pretty off from normal. Like, it's an abnormally low grade if it's 60, and abnormally high if it's 100. If you did 3 standard deviations, you get 110, which is a crazy score on a test. And if you get 3 to the left, you'd get 50, which is a really bad score on a test. So the further away you get, the bigger this z-score, the more unusual that score is, and unusually high or unusually low. But 2 and -2 are kind of a rough standard. That's a lot of the times that's what they mean by unusual amount to the left or to the right of the mean. So remember, a negative z-score tells us the data is below the mean, while a positive z-score tells us it's above the mean. So if you forget which order to subtract, use common sense, above or below, positive or negative. Like if my mean is 80, and my standard deviation is 10, and my point is at 90, it should be positive, right? It's above the mean. That's positive. And my point at 70, that's below the mean, so I should get a negative z-score. So remember it like that, and you should be good. All right, that is going to be the lesson for today, and we will